Hey future engineers, I'm John Santos, and welcome to the CFD tutorial where we simulate airflow over an airfoil, specifically the NACA 2412 airfoil. And we're going to be using scFlow. So whether you're working on a school project or just curious about how to do aerodynamic analysis digitally, this one's for you. Today, we'll go through all the basic steps in scFlow, from pre-processing down to the SC monitor and visualizing the results. So at the end of this video, I'll be giving a bit more information as to the results that we got from our simulation. Okay? So with all that being said, let's jump right in. Okay. So right now, as you can see, we are now in my desktop to begin our tutorial. But before that, I would like to point out that my mouse right here is actually surrounded by a color red or opaque red to make it easier for you to track my movements inside scFlow. Okay? So apart from that, I'll also be using a tool to zoom in. I'm going to zoom in, there we go. In order for you to see small texts like this. Okay, as you can see, it's V 2024.2. That's version 2024.2. Irrelevant, but at least it's an example that I can zoom into small texts. Also, you can see my cursor, it's color red. Okay, okay, remove that. So now to formally begin our tutorial, we'll be starting by launching our scFlow preprocessor. This is actually where we will be preparing our model and simulation settings. So that should be the first icon here in our scFlow kicker. Okay, so click on Launch Preprocessor. There we go. It is now loading, and we should be greeted by a GUI. There we go. It's the Select Project GUI. In here, you can use, well, you can click on project files that you have done before, or if you're creating a new file, you'll have the ability to name that project itself. So go ahead and put a name that is meaningful for your project. So for mine, I'm gonna go ahead and simply put in NACA2412 um, airfoil or underscore airfoil underscore sim for simulation. Simply click on create. But before we do that, or before I click create, I'm gonna go ahead and minimize my scFlow kicker here since it's still floating on the top left corner. And on the bottom right corner, I believe you can still see me. And I'm actually a bit of an obstacle towards what scFlow really is. So I'm gonna go ahead and disable my camera. So give me one quick second. Okay. So right now, I am no longer in the scene itself or the screen, but I'm still here with you, and my voice will guide you through the process. So continuing, click on Create. There we go. And we should now enter scFlow preprocessor with a blank workspace. So just to be familiar, this is going to be our workspace. Okay. This will be the workspace, the one with the graduation cap here. And this will be our part three. Okay, this is our part three right here. We're going to be clicking here for specific options. Once again, it is going to be parts. Okay, it's going to be our parts. And apart from that, I'm also going to be referring to this tab right here, the navigation tab. It contains our prepare parts folder, which is dragging down parts control, import part file, create parts, etc. Okay. And we're going to be actually, here's a hint, we're going to be going through down this list as a proper process to our simulation here in scFlow. Okay. So to begin and give a bit of start with our tutorial, import your part file. Okay. So just to show you once more, I clicked on import part file. It's right here. Okay. And it showed me a GUI here. It popped up my folder file. So go ahead and look for your NACA or my NACA 2412. In this case, I'm going to be looking for it. There you go, documents, Airlab. Okay. So, if you have a chosen airfoil or you were assigned an airfoil, whether you grab it online or make it through SolidWorks, it should be used here in scFlow. It should be compatible with scFlow. So, whether you're using an STL file, I believe, for SolidWorks, uh, or you're going to be using IGS. Personally, I'll be using IGS. So I'll click on IGS. And just to show you that this NACA 2412 right here is what I'll be using. I actually made it earlier before recording this video. This is the NACA 2412. Okay. It is, well, it's lagging, but there you go. It is the NACA 2412. I just quickly made it here in SolidWorks. If you're interested in me uploading a video in how to simply make a 3D airfoil using SolidWorks, I'll be more than happy to create a video for you. Okay? So going back, using that NACA 2412, which I saved as a IGS, I'm gonna click on open. There we go. It should now be executing the translation. And so, yeah, there you go. It is now showing my airfoil. It is currently colored green. But yeah, apart from that, that is what we're going to be using for our object to be interacted with within scFlow. So right now, you might be asking, just an airfoil won't do, right? So we're going to go ahead and click on Create Parts right here, Create Parts. Okay, and we're going to be prompted with another GUI, and it is already by default named as cuboid. No worries about that. This right here is our fluid domain. Okay, so the fluid domain around the airfoil is what we're going to be using to be the air volume where we will simulate the flow. So it is once again usually a rectangular box enclosing the airfoil with enough clearance, okay, or clearance. Sorry about that, it's clearance. So click on airfoil just to indicate that this will be our object, and this will be the center of our cuboid. So click on your airfoil, calculate size from selected parts, and the XYZ tab, well, earlier they were zeros and ones, but the XYZ for position and size will now be showing you information about your airfoil. That should be our goal there. And to make the rectangle itself, click on Extend Surroundings. Okay, so as you can see, my airfoil is sized at 1.5 meters. So what I'm gonna go ahead and do is show you that if I put in, let me see, many using scFlow actually put this as a bunch of ones. So that will be the minimum side and the maximum side for your cuboid. Let me show you that right there is a cuboid. The red, uh, the red object surrounding or encasing our airfoil is actually what you would call our cuboid. Okay, so give me one quick second just to recenter this for us. There we go. Before you do click on OK, you must, and this is actually important, register it as a fluid region. Okay? So register this as a fluid region or fluid region. Let me go ahead and zoom in on that. Click on register as fluid region so as to avoid any complications moving forward in our scFlow preprocessor. Okay? So click on that once again. And after it has been ticked, check if everything is to up to the instructions itself, and you should be seeing or mostly seeing the same thing as me. So just to clarify once again, these parameters right here, the X, Y, and Z for my minimum side and maximum side, these are going to be catered towards my airfoil. Your airfoil might be smaller, it might be bigger. Feel free to adjust it to what is um to what is needed for your airfoil. Okay, let me actually quickly show you if I put this as 0.75. Okay, 0.75 and make all those 0.75. I'm going to show you it became smaller. Okay. Sometimes this is a trick for lower end units or PC or laptops. You can actually minimize the size of your cuboid to help out with your CPU or GPU, whatever processes the simulation itself. So as for mine, once again, I'll be using 1. And if you do increase it from, let's say, 1.5 or 1 point, or let's say 2, it will increase as well, okay? So I'm gonna go ahead and place in 1. Once again, if you increase the numbers here, it will increase the size of your cuboid. If you decrease, it will decrease, okay? So click on OK. Once again, register as a fluid region. Click OK. It should now turn green. So as you can see, your cuboid has been made and your airfoil is inside your cuboid, okay? So the next step that we're going to be doing is actually defining our cuboid. So earlier, I mentioned that if you click fluid region or register the cuboid as a fluid region, it won't cause any complications. One complication or hint of a complication is that the cuboid, upon clicking cuboid, you should be given information as of its property or its properties, the part name cuboid, and the material in my screen is blank since I clicked on register as fluid region. If yours is showing as an obstacle, just like this, see that? For my airfoil, it is an obstacle since it will be the object that will be interacting with. If the cuboid is showing that this is an obstacle, please go back to the steps that we did earlier and make sure that you click on register as fluid region. Okay? Register it as a fluid region and it should show here as nothing. Since in this step, we're actually going to be assigning the material of that cuboid. Okay? Or what is inside that cuboid that will interact with our airfoil. So if everything is the same as mine, material is blank, go ahead and click on the 3 dots right here to give you more options for our material. So by default, it should be showing solid. Okay, it should be showing solid materials. Those are going to be pure metal, insulator, semiconductor, glass, etc. Anything that can be solid. We're going to be making it a fluid, okay? We're going to be giving it an attribute of a fluid and a material of a fluid. Those fluid being gas or liquids. They can be in both incompressible or compressible, up to you. They can be both temperature dependent or Sutherland's formula, up to you, okay? But for this project alone, I'm gonna go ahead and click on gas incompressible and air incompressible. Simply clicking on it does not do anything. Okay, or simply clicking OK does not do anything. Make sure you click on apply. Okay, so if you lost me there, when we were back in solid, click on fluid, click on the plus icon here at gas, or click on, yeah, actually click on the plus sign here in gas. It should drop down more menus or more options for what is specifically the incompressible gas that we're going to be using. Click on air, then click on apply. Take a look at here, cuboid attribute null and material null or none. If I click apply, it should now show as cuboid attribute is a fluid and the material is an incompressible air. Then now we can click OK. Okay, so and go ahead and go back. So the next thing that we will be doing is after giving a bit of specification to our cuboid is, well, before that, I think it's best if I mention to you if you have specific instructions or specific, let me see here, things that you would like to do in your scFlow, such as the angular position, mainly pertaining to the wind or the airfoil. Go ahead and look at here. It's going to be the angular precision, the ratio of edge length, the maximum edge length, the reference value, anything that you would like to tweak to your preference to make it more accurate, or what do you call this? To have your airfoil curvature correctly captured by the surface mesh. You can actually use the measure slash faceter settings, okay? So where did I click once more? I'm gonna show you. That's going to be measure slash faceter settings. Okay, click on it. And for my project here, everything is up to what I actually need. The angular precision is at 10, and those things are by default. Well, I don't really need to adjust anything. What's important here is if you take a look at this, the method for building an analysis model, which we'll be doing later on, it's set to be analysis model wizard. So there's another option here, which is SCTP v12 compatible. But what we're going to be using is analysis model wizard for our analysis model. Okay. So apart from that, click on OK if you have any specifications. This option right here is there for you. Okay. So after the what do you call this? After everything from material to the mesh and faceter settings, what we're going to be doing now is building that analysis model that I mentioned earlier. So click on Build Analysis Model, and it should prompt you with a message saying Build Analysis Model from parts. If the parts are overlapped, the lower part in the part 3 will be used. Okay, so simply click OK, and it should now be creating that analysis model for you. Okay, there we go. As you saw earlier, it gave me a quick breakdown of a mesh, then turned back as a blue. So earlier it was color green, now it is color blue. And if you notice right here in our navigation tab, we can no longer click on import file, create parts, modify parts, or measure faceter settings, since we have now moved on to our analysis model. So if you're not yet satisfied or have not yet accomplished any specifications needed for your parts, simply click on return to prepare parts before moving forward. Okay, since later on, if you have missed something that is specific to your project and moved on to this step, and if you click on return to parts, there will be a warning. Okay, this will reset any modifications of regions, which would be such a hassle since your effort would have been wasted in editing your analysis model. So please make sure to uh, well, specify or satisfy the requirements for your parts before continuing. Okay. Once you're satisfied and moved on, we can go ahead and build our analysis model. So to begin, we're gonna go ahead and actually click on surface region. I no longer need to zoom that in since it will be highlighted blue. It is under our part 3 region, surface region. Okay, there you go. I double clicked it. It showed me here a GUI register region and surface region. So what we're actually doing right now is we're going to be registering our regions along with the airfoil as a wall, and essentially the surrounding air as our fluid domain. Okay, so the reason as to why we're doing this is later on we're going to be creating boundary conditions and labeling our faces, or this is what I meant by face. It says face 0, face, another face, another face, another face. Yeah, those are faces. It will actually give us a bit of separation and accessibility to giving conditions to the faces that we'll be labeling. Okay, so to start our region registration, go ahead and click on the front part of your cuboid. That should be the phase uh, 2. Okay, phase 2. It should be the front of your cuboid as well as it will be the front of, well, the front facing the airfoil itself. Okay, the front of the airfoil. So I'm gonna go ahead and name this as inlet. Give me one quick second. I'll name this as inlet. There we go. And see here, yep, just click on register. Okay, register. Now that should be my surface region for the uh, phase 2 or the front of our cuboid. It is now registered as an inlet. If we have an inlet, we have an outlet. So the outlet, of course, would be the opposite side of our front, going to be the back side. It will be the trailing edge now of the airfoil. So go ahead and register that under the name of outlet. Register phase 5 or the back. There you go. You now have an inlet and an outlet. So to better give a proper image for our wind tunnel or the casing for the wind tunnel, we're gonna be registering the walls as well. So that would be the side, the left, the right side, the top, and the bottom as your walls. So go ahead, register those under the name of walls, and there you go. You now have an inlet, an outlet, and walls. So next that we're gonna register as a region is our airfoil as well. So some have shortcuts or techniques that are able to click on the airfoil. As you can see, if I try to click on the airfoil, I click on a face of the cuboid. Okay, same thing might be happening to you. So what I simply do is I disable my cuboid. Yes, you can do that. Go ahead and disable your cuboid for this quick second. There you go. I no longer have my cuboid and I have access to my airfoil. The reason as I'm doing this is apart from being able to access the airfoil, I can actually see better the blue the airfoil that is highlighted in blue or unselected regions of my airfoil. As you can see, if you're looking at it in this uh, percent of zooming, we can actually say that it looks good. It's better. But if you zoom in, let me go ahead and zoom in, there's still a part of our airfoil that is still highlighted as blue. Click on that, okay? This might not be the same case as to your airfoil. Maybe you did it in another way, or you have more inconsistencies here, or uh, more relations to your airfoil to create this curve. Unlike mine, it is smooth from top to bottom. You might have a line here to create this curve, another line here to create this curve. You're going to be needing to click all those. Most important here is going to be the trailing edge. Most of the time, airfoils that are put here in scFlow are, well, like that. It is highlighted in blue, and it actually causes complications for your simulation itself. It messes with the airflow. So go ahead and click on that to close the whole airfoil, giving it a bit of a skin for its interaction with the fluid inside our cuboid. Okay, so enough talking. Go ahead and just register that as airfoil. There you go. So I now have here 4 regions registered for my project. It's going to be the inlet, the outlet, the walls, and the airfoil itself. Okay, go ahead and close that. And if you would like to, click your cuboid back in, but I'm gonna leave mine disabled for now. Since the next step that we're going to be doing is we'll be registering the numerical region. Okay, so this will be the numerical region. It is still under our region here in the part 3. So after surface region, we move on to numerical region. If you double click that, you're actually going to be seeing the same GUI earlier, but you were moved to, or we are moved to the volume region. Don't get it confused, since um, in my first attempt here using scFlow, I was looking for numerical region within this GUI. It was just simply here. Okay, let me show you. If you click uh, under target, selected part, it should drop down the option of a numerical region. When you click that, no options will be shown here apart from creating a new numerical region. So go ahead and click and create a new numerical region. So for this GUI here, what will happen is, of course, let's give the region a name. I'm just gonna go simply name mine as number x, so numx, and specify the type to be a cuboid, since what we're using is a cuboid, not a plane, not a cylinder, not a sphere, or a combination of, what do you call this? Combinations. But I'm gonna go ahead and click on cuboid, and you're going to be seeing something a bit familiar. Okay, so in here, we're going to be given the option of either registering the numerical region inside of the cuboid or outside of the cuboid. Of course, we're going to be registering it inside of the cuboid. And earlier, the reason as to why I did not place the cuboid back in or enable the cuboid to be shown once again in our workspace, because I'm going to go ahead and click on our airfoil once more. Okay, so if the same thing is happening to you, I clicked on the airfoil, but it's registering here as the cuboid being clicked on. Go ahead and just click on the multi-BREP or BREP, multi-BREP. Click on it and select the option calculate size. Okay, so you can see some familiar or similar information as to what you saw earlier when we were preparing parts, since we are now going to be working with the airfoil once again. So you'll see information about the airfoil, calculate from the size, and extend the surrounding. This time around, earlier I used the minimum side and maximum side as 1, right? But this time I'm gonna go ahead and use half of uh, the size itself. Later on, I'm gonna go ahead and show you what I mean. I'm going to place in zero point 0.5 here for X, Y, and Z as my maximum and minimum side. I'm gonna go ahead and show it to you as a preview. There you go. So that's a preview of my sides right there. Okay. If I enable my cuboid, you'll be able to see that it is less than the area of the cuboid. Okay. So it's essentially up to you and up to what your airfoil size is or object size is. For mine, I'm happy and comfortable with my airfoil being inside a zero point 0.5 by zero point 0.5 surrounding for my numerical region. Okay, so I'm gonna go ahead and click on OK. And it should now give me another option here or another information here under volume region. Earlier, it was blank. No options were there, but now it is showing a region name of num x or number x. Okay, that was what we did earlier. Go ahead and close from that. And if you're having any trouble following so far from our tutorial, feel free to rewind the video, since what we're going to be moving towards to now is our conditions. Okay, so we are now done with preparing our parts along with registering our regions. We're now going to be making conditions, since, as I mentioned earlier, we were registering regions to make conditions. So simply click on conditions, okay? Assuming that you have no problems and we're continuing with the tutorial, click on conditions. You can click on conditions or press C on your keyboard or look at the top of your scFlow, and it should also give the option as condition. Click on condition as well from that. So from here, what is important is the boundary condition here, boundary condition, since we're going to be working with the flow boundary and the wall boundary later on, along with the output setting of analysis data, which I'll be explaining later on as well. So for for let me see here. For our analysis condition, simply look at the analysis type. Make sure that flow here is ticked as analysis type. Apart from that, nothing else needed for my project. Maybe something about yours. Diffusion, multi-phase, up to you. For mine alone, I'm just working with the flow itself here. Okay, so flow is ticked. Next, moving forward, boundary condition. This is where the the registration of regions come in. So I have the inlet, the outlet, the walls, and my airfoil. So in our inlet, as you can see, I clicked on inlet. We're going to be giving it a new condition. It's going to be the inflow condition for our inlet. So the name is going to be flux, set it as it be. Not really important. What's important is the normal velocity right here. It's highlighted blue on my screen, hopefully in yours as well. It's currently set to 0. That means the fluid velocity inside our cuboid from the inlet is 0. So we're going to go ahead and give it some speed, give it some life, and I'm going to set it as 250 meters per second. Okay? Go ahead before I click on set. Make sure that you're looking at the same page as I am inside this condition wizard. Okay? Boundary condition, flow boundary, inlet, then inflow condition, and we're now here in normal velocity set to 250 meters per second. Okay, don't click on finish, just simply click on set, since we're going to be working with the other walls as well, or faces. So of course, if we have an inlet, we have an outlet for our air. Go ahead, click on outlet. I'm just gonna go ahead and set it to 0 for the velocity itself since it is an outlet, and just let it be as default. Next, for the walls itself, this was actually what we have earlier or what we did earlier for the sides and the bottom and the top. It will not be within our flow boundary since no wind will ideally no wind should be flowing from any wall. Okay, we would like for the wind or the fluid to be what do you call this? Mm, Streamline from the inlet to the outlet. So we're going to be putting in a condition using wall boundary. There we go, wall boundary. Click on walls and new condition, it will be wall shear stress condition. So right now, what you're going to be seeing is the parameter value. The parameter is stress. The value is no slip. What we're going to do is click on no slip. Essentially, it does not show you any option, or originally, it does not show you any option for you to click on. It simply just looks like an Excel table. Click on no slip. It should give you another option, a drag down option, or labeled as free slip. Click on free slip. Okay. Now, same thing goes, the parameter is still stress, but this time around the value is free slip. Go ahead and set that to be the condition, and we will give more definition to the walls itself. So, going or moving forward, click on output setting of analysis data. Okay, it should automatically put you to output of field file. So, in here, what we're going to be specifically looking for is setting a surface data for our wall. So, give me one quick second. There we go. It is now zoomed in towards the surface data. As you can see, I was given more options when I click surface data. The reason as to why I'm zooming in is to help you out a bit more, looking for what I'm going to be clicking. So under variable, moving down, you'll be able to see wall shear vector. The output setting is default, which is do not output. We're going to change that. Click on wall shear stress vector, and you have here the option to set it to an output. So click on output. There we go. The wall shear stress vector is now set to be an output rather than the default do not output. Okay, so that should actually all be what is needed for the output setting. Okay, so just to recap before we move forward, we used the phases that were registered earlier as regions to set conditions to each of those region itself. We started from the inlet, going to the outlet, and towards the wall, under wall boundary, and set an output of field file under surface data directly towards wall shear stress vector. Okay, hopefully I have not lost you yet. And you should be on the same step as I am. After doing all those, click on finish, since we are now done setting conditions for our uh, project here. So before we move forward, please make sure everything is up to what I have shown you, or you have completed any requirements needed for you as instructed for your school projects and such. Okay? Since now we're going to be moving towards the octree parameter here. So as I mentioned earlier, the pattern with the navigation is the process, not the pattern, is going from the top to the bottom. We imported the part file. We created a part known as the cuboid. If you actually have a specified setting for the faceter, you use this option. Then we built an analysis model. After building an analysis model, we registered regions, as you can see, and we used earlier to create conditions. Okay, so after those have been done, we can now continue to the octree parameter. If I may have your attention here towards our workspace, it is currently colored blue. If we click on octree parameter, I'm going to be using the default 100,000 for the target number of elements. If you have, once again, something specified or you'd like to minimize that size, click on minimum size. But for my project here, I'm just using the default 100,000 and creating that octree. Click on create octree, give it one quick second, and you should now be seeing pink or peach colored cuboids outlined by pink or purple or neon purple, and inside would be your airfoil along with your cuboid. Okay, so a bunch of cubes. So after that octree parameter, we're now going to be setting our mesh parameter. Okay, so for our mesh parameter, click on mesh parameter once again. Let me show you. That should be mesh parameter, just right under octree parameter, all below conditions. Okay. So for our mesh parameter, it does not really, I'm not really instructed or given any specification for the thickness or the number of layers. Don't get me wrong, a lot of educational channels in YouTube show you a bit more uh, detailed tutorials in creating a mesh parameter that is very, or to say highly accurate. It actually gives you a better mesh model. But for my project here, I'm going to go ahead and use the default by scFlow 0.2 and the number of layers of 2. But once again, if you're looking for a bit more detailed explanation in terms of the mesh parameter, which I know some actually uh, do this for a living, they teach in YouTube how to make a better mesh parameter. Okay, so right now mine is actually set to just the thickness of 0.2 and the number of layers as 2. Okay, what's important is it's model shape oriented. I'm gonna go and create that mesh. There you go. And I'll explain right now after this loads. Actually, let's give it some time to load. Okay, so now that our mesh parameter has been generated in scFlow, as you can see, it has this honeycomb style here. It is actually going to be, if we rotate and look at the isometric view of our workspace right now, you're gonna see that it is surrounded by this honeycomb pattern. That is actually uh, what we're going to be considering as the mesh. Okay, click send. Let me show you the top here. So you can see the bottom, the sides, and our front. It's going to be all surrounded by this mesh. So earlier I did mention that some educational YouTubers get into detail in creating octree parameters and mesh parameters. Feel free to look for those if you're going to be into creating a better mesh and creating better octree parameter, okay? So as for this project right here and this tutorial, simply click on OK. And after all that has been done, what we're going to be doing next is executing. So we have run down from the navigation from the top, and now we're going to finally click on execute. So on clicking execute, you'll be prompted by this GUI right here. It says save files for analysis, mesh files, save it, analysis condition, save it, and save the project, of course. And based on my experience, if you click or if you um, untick the save project and still click on execute solver upon clicking OK, it will not give you that information inside our scFlow solver. Okay, so make sure what you have right here under execute the GUI is same as what I have here right now before clicking OK. Anyways, I'm gonna go ahead and click on OK and set up my recording here in order for you to see what is exactly happening inside the table in solvers. By the way, I did forget to mention before transitioning to the solver, after clicking OK, you'll be moved to another part of the GUI right here. It says execute the following task. Just click on execute and make sure that this is clicked. Okay, scFlow pre will exit when solver is launched. Actually, if it's up to you if you would like to unclick it or not. I'm gonna leave mine be. This will not close the scFlow preprocessor in the background, but if yours is having a bit of trouble loading the solver, make sure this is clicked and it will exit it for you, okay? Right now, I'm gonna go ahead and leave it blank and execute for us, okay? See you in the scFlow solver. Okay, so right now, as you can see, inside SC monitor, or in my screen, I can see the convergence status, which is a ratio of the relative fluctuation to this cycle itself. Right now, as you can see, everything is moving. And also, I did uh, move a bit further in terms of the process, but essentially, we're still all looking at the screen for SC monitor. Yours should show a job scheduler, a job message along with job property, a bit of information, but what is important in my case, I will only show the convergence status. Okay, so as you can see right now in my screen, it stopped moving for the convergence status, and I believe it won't pop in the recording. A closing message did pop up. It says reached steady state normally 50 cycles and a calculation time of 52 seconds, which is encased as 1.04000 seconds per cycle. Okay, so I'm gonna go ahead and briefly go through how to read the data of your convergence status or my convergence status. So as you can see here, there are colored lines. Those are going to be red. Let me go and disable everything first as well. You have red, you have green, you have blue, pressure, which is color yellow. You have purple for turbulence energy, and the specific turbulence dissipation rate, okay, or the black line. So. to give more information as to what the u velocity, v velocity, and w velocity, they are the symbol is going to be u, v, and w, but they are read as in terms of the direction. The u velocity is going to be our x-axis. It is the velocity in the horizontal direction. It is usually aligned with the main flow direction. Okay, that will be the horizontal direction from the inlet to the outlet. Next, you have the color green, the v velocity. The v is a symbol for the y-axis. It is the velocity in the vertical direction, the up and down motion that is experienced within our fluid domain. Next, we have the color blue line, which is the w velocity. The w is a symbol for our z-axis. It is the velocity in the depth direction. It is out of or into the screen in a 3D model. Okay, so those should be the u, v, w velocity. Okay, so what does the graph tell us? Let me go ahead and show everything once more. So in terms of the early cycle, most variables begin with high fluctuations, as you can see. It is going to be normal. There is a spike in turbulence related parameters that is going to be particularly the turbulence energy and the specific turbulence dissipation rate, which is expected as the solver stabilizes the turbulent flow field, as you can see here. It stabilizes. In terms of the mid-cycle, by the way, the cycles that I'm referring to are going to be here. As you can see, mine is from 1 to 50, maybe yours as well. But when I said early cycle, that will be 0 from the origin going towards the 10, which is around here. And next we have the 10 to 30, so that's from here going to around roughly here, okay? Here. So this will be the mid-cycle, early cycle going to mid-cycle. All lines begin to level off and decrease steadily. So from here, they decrease, no longer going up, but rather going down. So they begin to decrease steadily. Let me go ahead and show everything as well. See, everything has started to fall off from the 10 to 30 cycle. So the mid cycle. The pressure itself, let me show you the pressure. There you go. The yellow dashed, you see here, dashed line converges the fastest, reaching below -5. See here, -5. This right here, this is -5 in comparison to everything. See, it is the first to reach below the -5 early, which is excellent in my case. In terms of the velocity components, once again, the U, V, W, they all settle around the -3.5 here, -3.5. So that's here to -4, which is acceptable, as I would say. Okay, so moving forward to the late cycles, that is going to be 30. Let's see here, 30 to the 50s. So 30s to 50s. We're going to go ahead and, as we can see here, we can read it as a continued reduction in fluctuations across all variables, specifically the u velocity for the x-axis and pressure. Let me go ahead and just show those. They stay consistently low. It actually indicates a good convergence in the direction of primary flow. Okay. Next would be the turbulence energy and the dissipation rate. They gradually decrease. Okay, so from the 30s here, going to the 50s, they gradually decrease after their earlier spikes, showing that the turbulence model has stabilized. Okay, as I mentioned earlier. So, uh, let me go ahead and show you once more every information that we got here in terms of our relative fluctuation cycle ratio. So, most relative fluctuations are at or below -4. Okay, or yeah, here. Those are going to be what's most relative. As you can see, they are dashed. If you can notice, even down to our red line here. See, it is starting to be dashed since it entered below -4. Okay, so it is a typical threshold in the CFD or in CFD to consider result stable or results stable. Okay, so pressure and velocity values are particularly well behaved for the NACA 2412, and minor turbulence spikes early on are expected and do not indicate a problem as they settle later on. Okay, once again, they settle later on. So, apart from that, I believe that is going to be the end for this tutorial, since we now have a visualization of our results, that being the convergence status. Okay, let me just go ahead and switch. There we go. I'm now back in the screen itself. That has been our tutorial for CFD, CFD simulation for, well, using scFlow. So once again, this is going to be the end for our CFD simulation using scFlow on airflow over an airfoil tutorial, specifically the NACA 2412. So I hope you enjoyed the video and found it to be educational. And apart from that, I believe we did not miss anything else. So thanks for tuning in, and I hope this helped you understand the workflow in scFlow. Until next time, keep exploring, keep flying, and goodbye, future engineers.